All right. So before we begin today's lecture, especially because last time it was pre-recorded, I want to take a little bit of time out if anyone has any questions from the previous lecture. Anything on what we learned in terms of theory, or if there's any issues with the coding portion. Happy to chat about it now.
I had a couple of questions about the assignment. Would you be able to maybe, I didn't catch your office hours. Do you have a fixed time for that, or do we get an appointment?
Oh yeah, so office hours were actually from 1 o'clock to 2 o'clock today. But that's okay if you want to meet separately, and I guess we'll probably have a little bit of time at the end of class today. I'll maybe address one or two things on the homework, and then if you have any questions, then I can we can do that. But let's hold off on homework questions till the end of class. All right, so it seems like we don't have too many questions. Everyone's got perfect knowledge already of the material from last class, so that's good. Okay, so to start off today, let's talk about outliers. So we've sort of been introducing concepts in our sort of first approach of linear regression, thinking about interpretation, how it's estimated, common metrics to measure the sort of quality of the model. And so the next thing that we're going to think about is essentially thinking about outliers and how you can sort of deal with them in the data set. And so to kind of start off, I'm going to introduce a couple of terms and measurements of how we can even sort of qualify something to be an outlier. And then we'll kind of look at this a little bit more in detail in the code itself to see how it can be applied. Okay, so the first term that we'll talk about is known as leverage. So this is how much would the predicted value change if the observation was shifted 1 unit in the y direction. So this is always between 0 and 1. And the way this is measured, so HII is what we denote as leverage, is equal to the change in my predicted value divided by the change in your observed value. So essentially, you're going to take a point and you're going to shift it by 1 unit in the y direction. And in doing so, you'll see that your predicted value is going to change by some amount. And so the proportion that it sort of changes that particular value is known as the leverage. You can imagine, let's see, that points are going to have a different amount of leverage. So I'm just going to draw a couple points like so. And let's add, let's for example, think about a point right here. And so the whole idea is that if I shift this point up by 1 unit, that should, in theory, slightly change my my line. Okay, and so you can imagine how much. Well, let me actually draw this in blue. You can imagine how much like that proportion of that change is caused by that particular point, and how that may differ. For example, if you had, say, a point way out here that went up, right? That may have a somewhat larger effect on your regression. And so the amount of leverage that a point has can be one criteria in determining whether or not that point is an outlier. And again, we're going to look at this in practice in a moment. Okay. There are a couple other ones that we'll look at. So the other one is going to be influence. It is a term called influence. Some of you may have heard of its other name, which is Cook's distance. So this is the effect of deleting a point. Okay, and I'll give the equation, but like kind of most equations here, this is mainly for your reference. It's not something that you're going to be expected to memorize. So di is equal to di standing for the distance for point I. Okay, this term on the right-hand side is the fit yi hat without the point yi. Okay, and so we're going to see that the way influence is measured also looks for outliers, but that leverage and influence kind of look at points a little bit differently. And we're going to be able to see that in the examples that we give. Okay. Any questions about this so far? All All right, so let's jump on over to the R Studio. And we are going to do our typical regression data set again. So hopefully everyone is kind of thoroughly familiar with this. We're going to make up some points here. So 100 randomly selected X points between 0 and 50. We're going to introduce some random error, which is a normal distribution. Mean of 0, standard deviation of 5. And then we're going to create our X or our Y via this function. And let's go ahead and just plot it, see what it looks like this time. Okay, so we've got our data that looks like this. And now what I'm going to do is I'm going to add a single outlier. Okay. So what I'm doing here is I'm going to take my X vector and I'm going to concatenate to my X vector a single point, and it's going to be at X value of 100, and I'm going to do the same for my Y, and that'll be at 20. And so to give you a visual of what this looks like, so it's going to be the exact same plot that you see here being displayed, except it's going to, we've now added one outlier into it. Oops, I need to actually put it in. Okay, so in this case, you know, we can plot it and maybe you would intuitively be able to see this, but the strength of the tools that we talked about, the influence and the leverage, is that, you know, I can apply this to regressions where you have multiple variables, or where the outliers may be a little bit less obvious, less easy to see sort of visually. Okay, and so let's see how this kind of influences, no pun intended, model. So if I were to, okay, actually, if I were to, I'm going to actually make this example model 2 so that we can see what it looks like here before we add the outlier. I'm going to have to rerun everything. The plot's probably going to look a little bit different. So here we are again. And we can see our estimate. Again, we know the true value of the coefficient is 0.5. So it's 0.51617, fairly close. And we can see what adding the single outlier ends up doing to my model. So I go from where I am about, you know, 0.17 away from the true value down to, or up to a difference of, you know, 0.7, 0.8, or 0.07, 0.08 away from the true value. So that, so the slope of the line ends up essentially getting pulled down a lot, right? Because of the effect of this outlier. So let's take a look at leverage. So the way this is done in R is with this function called hat of your model matrix. And actually, if you'll remember, the mathematical notation is this HII, and so that's what the H stands for. It's the hat. And so this is going to return the ratio between how much your prediction changes at each y point for every point of data, right? How much your prediction changes relative to a 1 unit change in your y value. So this gives you a vector of leverages corresponding to every data point in your data set. So I can run that, and we can go ahead and take a look at what this looks like. So you have a whole sort of bunch of points here. And let's take a look. If I just plot my leverage, it looks something like this. And if I plot x versus the leverage, uh-oh, what's going on here? Oh, I didn't rerun, did I? No, I did.
You maybe have to put in model 2 instead of model 1.
Ah, yes. Oh, good catch. Sorry. Thank you. Whenever you have these errors during class, I start panicking. Okay. Yeah, actually, and so hopefully this will give us a better sort of picture. Okay, there we go. So you can see that the point that we appended on at the very last one is corresponding to a point that has a lot of leverage. And you can see that being reflected in this plot here. So this isn't in any particular order. And I can plot it against my x's to see it'll be fairly similar. And you can see actually the influence of your x's is patterned by how it goes, the x's relative to its location along the fit. So it's going to look like this parabolic curve. And then your far out point is like really sort of abundantly obvious, right? And so you can kind of make a decision about what might be sort of considered an outlier based off of this metric. With leverage, typically you are doing some kind of comparison of the leverage points, and it is context dependent. And you're always looking at the relative leverage of your one particular data point compared to other data points. And that in itself can start to get a little bit tricky, especially if things are a little bit close. With Cook's distance or influence example, usually we think of characterizing it via a cutoff point. So let's just do this, make sure I do example model 2 here. So these are, again, a vector of influence values corresponding to each data point. And then we can look at the plot of this. Plot Cook's distance. Oops, hang on. I want to actually do this in up here. Okay. So here you can see kind of similar to the leverage. you have one sort of really one really obvious point that is outside of the sort of bounds of the Cook's distance that you're seeing for a lot of these other points. So if I were to essentially take away that one specific point, it is going to influence the model to a much greater extent than any other data point in the data set. For some reason, I don't have this in my notes. I'm trying to remember the cutoff point. I think it's around around 1 is when we start to think of it more and more of as kind of an outlier. But I will get back to everyone on that when I double check it. Okay, so these metrics are sort of the go-to common ways of identifying outliers. And then there's this other question then of what do you do about outliers? Okay, and so that is much more sort of art than science. And I think it also really depends on the context of the data set and the context of the problem that you're trying to address. You know, an outlier can be any sort of number of things, right? It can be something unusual that may not sort of follow the pattern of the data, or it could be something that indicates, for example, like an error in the data. And though the way that you would treat that can be really contextually different, right? So simply because something is happening in a way that's not sort of within the pattern that you might expect, when you try to train some kind of model to the data, you need to ask yourself, well, am I looking for a pattern just in the obvious ones, or do I actually want to include the outliers, right? Because it's still sort of real data, right? And so just because you've identified the fact that a point could be an outlier doesn't necessarily mean you need to sort of reject that data point and omit it from your data analysis. You should understand kind of what it's doing to your model fit, and whether or not that has implications in the way that you interpret like the slope of a line. You could say, this is what we find as sort of the average response, but also note that there's this really large influence being caused by several points. And so again, when we do this kind of procedure, oftentimes in some data analysis classes or in statistics classes, they'll just say, okay, just like drop the points and then rerun the model, right? But really, we want to encourage really sort of active thinking about what it means when you do identify an outlier, and whether or not it actually makes sense to drop that data. Okay. Any questions about that? All right. Nothing there. So let's go back to the whiteboard. Oh, I do see a question coming in. Okay, so is the hat, quote unquote, hat a dedicated function for leverage? Yeah, that's exactly right. That's what that hat means. And actually, we can let me jump back to RStudio for a second. If we look at the help function for the hat function, it will tell us So used to compute like leave one out deletion. So even here we can see that they're employing this as a way of deleting points, but you first have to identify the points. That's just what we're kind of leveraging it for. So influence measures, yeah, hat values are for influence. Well, okay, that's a bad way to put it, because we're talking about Cook's distance for influence. It's one measure of influence, but I don't want to confuse you guys. So hat is basically the function to determine leverage. Okay. So one common sort of misinterpretation of linear models is the fact that the variables within the linear models do not actually have to be linear. All a linear regression means is that the parameters must be linear in form. And so when we think about an equation, right, of, you know, x like this would not be linear, or y equals, you know, beta x1, x2. This would also not be linear. But as long as the parameters are linearized, the variables themselves can actually be sort of transformed in any sort of arbitrary way so that you can produce a linear fit, right? And so, for example, if I were to draw a set of points that look something like this, or if I were to draw a set of points that look like this, right? We might argue that a linear model does not kind of fit the functional form of the data very well. But in fact, you can always, or not always, but oftentimes, you can transform your x's so that you can do something like a log transform in order to essentially turn your data into a linear functional form so that you can perform a linear regression on it. And so this is really common, especially in the field of econometrics, to attempt to essentially linearize the data so that you can fit a linear function to it. And there are benefits to this type of approach. You know, we will get to talking about other forms of regression where you may, you know, try and actually fit through the data itself without any sort of transformations. But oftentimes those type of models are a lot better for doing things like prediction. where you want to say plug in new points and figure out what values those would be on the outcome. In a lot of sort of econometric and causal-based approaches, doing a linear regression allows for a much more interpretable sort of set of results. And for that reason, it is fairly common to do sorts of transformations on the data. And so we're going to talk about some of the sort of common ones in terms of log transformations and essentially how to interpret them. So the one that sort of form of linear regression that we've been talking about most often is kind of referred to in practice relative to these log transformations as a sort of level. And so what this looks like is I'm going to have something like y equals beta x1, okay, plus my sort of error term. Okay. And so what this tells you is as x increases by 1, then y will increase by beta. So hopefully everyone's able to follow this, right? It's basically just your slope, right? So if I add 1 to my x, then my y is going to increase by beta. Okay, so then we'll have something known as a log level. And so this is if I do, and when I say log, I'm basically always going to be referring to this as a natural log transformation, not a log base 10 transformation. That's just kind of how they do it in practice. Beta x plus epsilon. So in this case, as x increases by 1 unit, y will increase by 100 times beta %. Okay, so this is actually a nice little simplification for doing the interpretation instead of like figuring out what the log value change is. Essentially, a nice sort of rule of thumb is that as my x increases by 1 unit, my y will increase by essentially beta times 100%. Okay, so the next one is level. Oh, not level log. And hopefully you guys can imagine where this is going. So beta log x plus epsilon. So here, as x goes up by 1%, y increases by beta over 100. And lastly, for log, this is going to be, oh, I should be consistent here instead of writing log. Right, ln. So ln of y is equal to beta ln of x plus epsilon. And this is as x increases by 1%. Y will increase by beta %. Okay. This type of interpretation is very common in the field of economics and econometrics, as I was sort of mentioning before, because lots of things kind of grow exponentially. We linearize that by doing a log transformation, and therefore, because it's so common, folks have come up with this sort of way of interpreting it. But there's one thing that you need to be very careful of, and that's the fact that the reason why we can do this is because, so let's say I do ln of 1.01. Okay. So the log of 1.01 is approximately equal to, let me make sure I get this right, 0.00995, which is about 0.01. Okay, and so you can see where we're kind of getting at here, right? So the natural log of 1 is just 0. So if I go from an x value of 1 to x value of 1.01, I am increasing by 1%, and that corresponds to a 0.01 change, right? So you multiply that by your beta, and so you can see that being reflected as essentially kind of like a percentage change in the y. But but my 0.00995 is not exactly equal to 0.01, and so this is a fairly good approximation for marginal changes. But if you do sort of a large difference, then this interpretation will be slightly biased upwards. So important to keep that in mind, especially if you end up in a field that's doing a lot of this type of interpretation. All right.
Can I ask a question about this?
Yep, absolutely.
I'm just wondering, like, so if we have a data set, and if it seems like it's linearly related, we go with the level. How do we choose between the other three? Like, it's one thing if you have a model in mind and that you want to run. Like, if I already know that I'm going to take the log of y and then test that on x, that's one thing. But if I want to look at the data and then decide which one of these 4 to use,
yep.
What are we looking for?
Yeah, great question. So there's a couple reasons why people will log data. What I think the sort of 2 sort of common ones that probably don't require like a huge amount of investigation. So one is if your values are sort of one-sided, and in that like they're only allowed to take like positive values. So for example, for a lot of goods, you'll only have positive prices. There isn't really. I know that in some types of markets you could have negative prices, but generally if I'm selling like a car, for example, there's no such thing as like a negative price for a car. And to avoid this issue of going below zero, or like car sales, for example, where there's no such thing as having negative sales. Oftentimes people will log those values in order to keep the sort of distribution of the data from essentially going below zero. So that's one common way of doing, or that's one common reason for why people do it. Another one, and probably makes a little bit more sense, is if the relationship between variables of interest follow any sort of exponential growth. And I think this is probably the most common and most sensible, is that you could simply plot your x against your y and see whether the sort of relationship between those two variables looks kind of linear. And if it doesn't, if it's some kind of like squared polynomial or some kind of exponential growth, logging it will sort of generically linearize sort of any exponential growth, and then the rate of that growth is going to be determined by the beta. So it's a nice kind of generalization of transforming any exponential growth relationship between your data into a linear term. And so that's, I would say, the two sort of easiest things to look for to do this kind of transformation.
So if it's, let's suppose if it's increasing at an increasing rate, like if we put y against x and we just find an exponential relationship, do we take a log with the y or a log with the x? I've always been confused about this.
Yes. It depends on, right, your relationship. So in the x case, it should mean that the y's get larger and larger, right, as you move progressively down your x linearly. And then in your y case, it's the other way around. So let me actually draw an example of this, and hopefully that should make more sense. So okay, so this would be so this would be my x's are kind of constant, but my y's are increasing in size, right? So like these are getting bigger and bigger, but these are about the same, right? So this case, you would log the x value. Wait, no, sorry. You would log the y value. And then in the other case, it would be so your y's are fairly the same, but your x's get really large. So it would be something like, how would I draw this?
I guess like upward sloping and then just becoming flat as you go up.
Like kind of like this, right? So these will get farther and farther. So it would be like that. And then so log the x, and then the last one, which is a little bit less obvious, but actually this type of thing I actually see very commonly, is where you have like lots of points, and then like really, really interspersed points, right? This might be common for something like if I were to do population versus GDP, you have like countries that have really small populations and really small GDP, and then it gets dispersed to really, really large GDPs, really large populations in kind of like an exponential way along both axes. And so the like defining characteristic of this one, so log both x and y, is that you have these like growing spaces in between your points as you go both along your x-axis and along your y-axis. Okay, does that help?
Yeah, definitely. Thank you.
Yep. Okay. Why don't we, before we switch gears to talking about multiple regression, let's take a break until, let's say, 3:01.
Can I ask a question about the homework?
Let's hold off on the homework questions till the end.
Okay.
Yeah, I think we'll have some time to go over homework questions. Yeah.
Thanks.
All right, let's jump back into it. So the next sort of step in our progression is to talk about multiple regression. Multiple regression. So this is an extension of our simple linear regression. Where we predict the value of a response variable, but instead of doing this with a single variable, this will be based on the value of 2 or more other variables. Okay, so it's fairly straightforward. The functional form here is going to look pretty similar. We have beta 0, which we'll say is our intercept, plus beta 1, x1. I also have an I for the individual data points. But in this case, you may have, for example, 2 variables. So it would look like this. And this, the extension from linear, from simple linear regression with one explanatory variable into multiple linear regression with 2, that sort of analogy can be expanded to an arbitrary number of variables. And so, your equation ends up looking something like this. Beta 2, x2, I. So generically, you may have, something like an n number of terms. So beta n, x n I plus epsilon I. And so now your response variable is now a function of not just one, but several different variables. And the sort of graphical analogy I'll show here. So it'll look something like this, x, y. You could have a whole set of points that look like this, right? This is our regular linear example. And now we are operating in a slightly more complex space. So we're going to test out my 3D drawing skills here. Not easy to draw this in 3 dimensions. Okay, and then let's say I have some points, and I'm just gonna try and make it so, let's just say the larger points are closer to you. So it might be something like this. Okay, in which case you might imagine the plane looks something like this. If you can maybe try and visualize this in 3 dimensions, okay? And so I can actually, create this plane, and then I can independently think about my slopes, right, which are my betas. So then you'll have a beta 1. So this is, slopes in the x1 versus y dimension. And then you would have a beta 2, which is slopes in the x2 versus y dimension. All right. So let us take a look at an example of this in the code. So we'll do multiple variable regressions. And I am going to create this time, a couple different x's. And here, I think, is where we get to really kind of view some of the power of your linear regression, and being able to figure out essentially the effect of a specific variable, and really sort of see how well it can do it, especially in the context of data where we know relationships are linear. Okay. All right, so here I am creating 4 vectors, points for my x's. 2 of them, so x1 and x3, are distributed randomly between 0 and 50, and then x2 and x4 are distributed randomly between 0 and 100. And then we're just going to add some random error into each of the sort of points. And let's do y multi. So we're going to do 0.5 times x1. This is kind of exactly the same as all the examples that we've been doing before, that relationship. But now we're going to add in, let's say, 2 times x2 plus error multi. Okay, so now I have a set of x's and a corresponding vector of y's. Let's quickly plot this just to see what it looks like. Okay, this line of code right here is for the base version of plot, which lets me create a window, a 2x2 window, so that I can fit 4 plots into it. So I'm going to plot each of my x's against the y. And, oh, I don't know why I put this here. That. Okay, so we can see there is a relationship between my x's and my y's that is particularly obvious in x2. But what's really interesting is that x1, which we've explicitly denoted here, right, as one of the variables that influences my y, it appears, right, kind of like these other ones. It may look like there isn't a relationship. And so this is kind of a visual warning for you guys, right? When we are talking about multivariate regression, the reason why this is happening, right, is that you have 2 times x2 versus 0.5 times x1. And so my y outcome is much more strongly influenced by my y2 than it is by, or sorry, my y outcome is much more strongly influenced by my x2 rather than my x1. And as a result, visually, when I look at it, I'm not going to see the pattern, right? And so this is a word of caution that as you investigate the data and you're looking at these individual relationships between your explanatory variables and your response variable, don't simply dismiss the fact that one of these could actually be playing a role in the y just because it looks like this. Okay. And let us example multi-model. And now what I'm going to do is I'm going to compare my y against all of the x's. x1 plus x2 plus x3 plus x4. And let's see what happens. So I run that. We'll run the linear regression, the multiple linear regression model that I've just defined. And now let's look at the summary. Oops, I think I accidentally ran everything again, but that's all right. Okay. So we can see actually that the linear regression is a really sort of powerful tool in honing in on something that leads to some kind of effect, right? We observe the true form of the relationship is 0.5x1 and 2x2. So x1 has 0.52, pretty close. This is actually similar to all the like previous examples that we've been doing again and again. And then x2, 1.995. And both are extremely statistically significant, right? You can see this value is tiny. Actually, I'm not sure if I sort of explained what the t-value was ever. This is the number of essentially standard errors or that it would take to get from your estimate to a slope of 0. So, actually 113 times the standard error before your x2 could be 0. So this is like a vastly, very, very small probability that it's that the slope actually would have a 0 effect. And then we can actually observe our x3 and x4, which we know do not influence the y. Neither of these are statistically significant. And so in this case, the model is actually doing a fantastic job, right, at being able to figure out, in this case, the sort of true effect. And again, kind of re-emphasizing, it is always really good to look at the data, but you can be sort of deceived. If I didn't know the answer here, and I were only to look at at the relationships individually of my x's against my y's, you're going to miss out on your x1 for sure. So again, just a word of caution when dealing with sort of multiple variables. Okay. Any questions so far? Okay. So nothing there. Let's go back to thinking about other sort of types of variables. Let me hop on over to the whiteboard again. So with the sort of log transformation variables, you know, we're sort of expanding to start to think about forms of variables and other sort of variable types. And so this is not in any way sort of structurally similar, but sort of in the same vein when we think about other forms of variables. One of the sort of common ones that come to mind are dummy variables and or categorical variables. So let's talk about these. And today, as we go through these examples of variable forms, types of variables, and multiple regression, we can really start to look at some practical examples to build up our intuition and also how we interpret the models. So, okay, a dummy variable is a variable with only 1 or 0 to indicate an outcome. So in other words, this is a binary variable. So really important in a linear regression, we can only do dummy variables and categorical variables, which I'll talk about in a second, as part of your explanatory variable set. Once we're talking about the response variable, like if you have dummy or categorical variables for y, we can no longer do linear regression. And I will get into that sort of later on in the course, and we'll figure out how to deal with that. But for now, I just know that when we're talking about dummy variables and categorical variables, this is really just referring to on your explanatory variable set. Okay, so what are some examples of dummy variables? So like flipping a coin, if you can only get heads or tails. Let's see, another dummy variable could be, you know, for example, like a demographic thing. So you could be like, if you've had a college degree or not, right? You could have 1 for college degree or 0 for not having a college degree, and so on and so forth. So the dummy variables help you, you know, break down your variable into only sort of 2 possible values. It doesn't have to be 0, 1. It can literally, it can be anything, but as long as there's 2 values, that's the most important thing to keep in mind. Okay, categorical variable. A variable that can take any number of discrete values. So this is kind of our extension of the dummy variables, except that instead of only having two possible values, you could have any sort of number of discrete values. So this could be a more generic set of education levels. So where I was giving my example before about whether or not you have college degree or not, this now you could have like, oh, no high school diploma, college degree, you know, postgraduate degree. So the categorical variable can take on more than just two values. Another example might be like a political party. So you could be, for example, Republican or Democrat or Green Party or independent, right? And so many levels. Okay, and the last one that I'll talk about is interaction variables. Okay, actually I realized, I actually, now that I'm writing this down, I realized that one of the examples that I pulled earlier on in the lecture, where I said it wasn't linear, actually is linear. If you have beta x1, x2, you can actually do this. You can't have like beta squared or like beta 1, beta 2 in here. But actually this form that I'm writing here is actually an example of an interaction variable. So sorry for that mistake. So this is 3 or more variables whose influence is not additive. So what this means is that you may have like an x1 and an x2, and they have some effect on y, right? x1 has an effect on y, x2 has an effect on y, but then you may have a separate effect on y happening as the result of the combination of x1 and x2. Okay, and so we're going to get into a practical example of this, and especially for folks who are kind of learning this for the first time, you know, the interpretation I've definitely found in the past to be sort of a little bit challenging. So please don't hesitate if you're confused in any way about how we go about understanding and interpreting the dummy categorical and interaction variables. So I'm gonna jump into the examples now, unless anyone has any questions.
Should the interaction variable thing be 2 or more variables?
Kind of. Okay. The reason why I write it as 3 is because the interaction term itself is, you can almost think of as its own variable. And so if you have 2 variables that have some interactive effect, it's essentially like having 3 variables.
Got it. Okay.
Yep. Okay. so we are actually going to use a real data set called wages. Okay, I'm going to use fread again, which means I have to load in my data table. And I'm going to read in. Ooh, okay, let's make sure we. I caught it this time in the right directory. Okay, yeah, wages here. So I need to set this as my working directory. And I'm going to go ahead and load in a small little data set called wages. And let's go ahead and take a look at what this data set contains. Okay, so the structure of it. So there's 6 variables. Earn, which stands for your annual earnings, height, sex, race, education, and age. And let's do a summary of wages. Okay, so we have earnings, we have heights, all kind of sort of make sense. We have sex, which is gender. This is another example of one that you could categorize as a dummy variable. Okay, I don't want to be like gender exclusive. So if we're just talking about sort of traditional male and female, that's when you could consider it a binary variable. If we include sort of non-binary, then it actually turns into a categorical variable instead. In this case, I believe in this data set, there's just male and female. And then you've got race, education, and age. So let's just quickly look to make sure. I'm going to look at the different genders. You've got male and female, and then the different race, which is you have white, you have other, Hispanic, and Black. Okay. So what I'm going to do now is I'm just going to go ahead and run an initial model. And then let's look at the results and think about how to interpret this. What I'm actually going to do here is I'm going to regress earnings on the age, education. So this form of education is not like as I was describing before, where you have a category of like high school degree, college degree, that sort of thing. This is just years of education. And because it's structured that way, we can actually treat it as a continuous variable as opposed to a categorical variable. However, gender is a categorical variable, and so I'm actually going to enter it as a factor. And actually, anytime you do it with strings, it'll factor it for you, but I want to kind of make it explicit so that everyone understands what's going on. And so when you do the factor, excuse me, remember that it is this kind of data structure that that's creating these sort of levels. It's essentially separating it out into these like behind the scenes values. So I will go ahead and run this. And let's take a look at the results of this. Okay. We've got a couple things to interpret here. And actually, maybe I could get a sort of volunteer to help me sort of walk through this. And so we can kind of communicate on what's going on here. So who wants to maybe help me out? Anyone?
I'll go.
Yeah, okay, great. Thank you, Aditya. So let's talk about the variables that we are kind of familiar with, or the variables of the form we're most familiar with, which are the continuous variables. So education and age. So tell me, could you interpret sort of these two lines for me and kind of walk
So
through?
so for every 1 year increase in education, the earnings will go up by about $4,470.
Yep.
Dollars.
Great.
And in case of age, for every 1 year increase in age, your earnings go up by about $281.
Great. Okay, perfect. So, you know, if I wanted to get higher earnings, right, I would prefer to have more education than to be old, right? Because we can see in the data that people tend to be, on average, it tends to be that education adds more to your earnings than age does. Great. Maybe you could talk, well, okay. Yeah, talk me through this intercept term. What does this mean? So strictly just in terms of the mathematics, what is the intercept telling us?
Yeah, so for all else being 0,
Yes.
The earnings point would start at a negative.
Great. Okay, perfect. So if I were, so it's a little nonsensical, right? When we look at the actual sort of spread of the data compared to the sort of 0 point, it extends actually beyond your sort of field of data. So this is kind of like extrapolating a little bit farther out. But the like true interpretation would be if I were 0 years old and I had 0 years of education, I would be starting at an annual salary of negative $48,000, right? So there is one kind of tricky bit about this, which is we also have this factor sex male thing going on here. So, okay, Aditya, do you know what this means? Like the intercept relative to this?
So for every time the individual is male,
Mm-hmm.
you would have a higher earning of 21,000.
Okay, yes, perfect. Yeah, okay, so thank you, Aditya. That's exactly right. And this actually means, well, what about if you're a female, right? It's not listed here. And that's because the intercept acts as the sort of default value for the gender and for any sort of categorical variable. And so the intercept, we actually need to extend our interpretation to be, okay, if you have 0 years of education, if you are 0 years old, and if you are female, then you would make this amount of money. Okay, and so we can interpret this as kind of the starting point, and then we can interpret the difference between the male and female as, on average, males make $21,000 more a year than females do, according to this data set. When we let me actually kind of take a step back and simplify this wage model. I'm just going to do the explanatory variable of gender. What's going on here? Oh. Oh no, what's going on? Wages. Oh, sorry. Okay, wage model gender. So I'm gonna, again, do this kind of step back and do this interpretation. So this means that on average, a male will make $21,748 more than females. And females at my intercept, which is my default starting point, should make about $24,000. So let's just draw my X and my Y. The idea here, right, is that in the linear regression, you have something like this, and I draw points through it. But in this case, it may actually look something like this. Let's see. And in fact, what you're essentially doing is you are drawing horizontal lines here, because your X's are just these fixed values. And so this is going to be for males, and this is going to be for females. So this value is going to be 24,246. And then this value is going to be 24,246, which is the female level, plus 21,748, which is the male level. So everything is going to be relative to your intercept, and your intercept is going to be the base value for anything, for whatever ends up getting omitted. All right.
Why do you have to type factor before the sex variable?
Yeah, so you actually don't have to do that, but behind the scenes, it will turn it into a factor anyways. What is happening is behind the scenes, it doesn't know how to do a regression on a character. That just, it's not, like, that's not something that that can be, like, there's no such thing as doing a regression on a word, right? And so what it does is it transforms it into a value. So essentially it's gonna, by creating a factor, it's gonna create a column. So so let's say our table looks something like this: M, M, F, F, M. Behind the scenes, what you don't really see happening is it will be doing this. It will essentially create, as part of the table, 1 1 0 0 1 0 0 1 1 0. That is essentially what happens behind the scenes. And I'm explicitly telling it to essentially do that by saying factor, but you don't need to write factor. It'll do it on its own. I'm writing it so that we understand what's going on. Okay. Let's clear this. We can see that, let me actually return to this guy. We can see that the model generally, right, if we go by our metrics of like significance, like the variables are all definitely making an influence. The R-squared might be a little bit low. Let's look at some other diagnostic measures, right? What's another important one? The residuals. Is there anything sort of systematically biased about this model? Oh, hang on. I'm still in the plot 2 by 2. Okay, there does appear to be something weird about this. We're getting this kind of cutoff thing here. This doesn't appear to be super randomly distributed, and the errors look like they're kind of getting bigger, which is a common thing you'll see as well. So let's see if we can maybe try and fix this. This is some kind of procedure that I would kind of think about when I see residuals that look like this. One of the first things that I would suspect is that you're doing this linear fit against sets of points where you're not really going below 0. And so this is the thing that I was talking about with the transformation. I know that the earnings typically aren't going to be going below 0. And so I'm going to try and log it. And this may delete like 1 or 2 points where it is below 0. I did see, for example, in the summary that there was like a negative 98, but that's kind of fairly unusual, right? Especially when we're talking about the sort of average annual earnings. So I'm actually okay with that particular data point getting dropped. And let's take a look at what happens. Okay, so we do have some NAs being produced, right? Because you're doing logs of negative numbers. So those end up getting dropped. So the interpretations are now different. It's like I said before, you're now doing this like beta % thing, right? So a single year increase in education is going to be a 16% increase in your wages and your earnings. For every year in age increase, a little less than 1%. If you are male, you make approximately 100% more than females on average. And so, you know, all of our interpretations are slightly changing here. I can't interpret the intercept without kind of doing this backwards transformation, unfortunately. And let's look at the residuals of this one. Okay, and now, compared to this one, where the spread is kind of really big, and you've got like a lot of points that look sort of outside the cluster, as well as this kind of sloped line where points aren't really exceeding that, we can see our residuals to some degree are kind of a lot better, right? I would say that everything here in the sort of top portion, let me just circle it actually. So this set of stuff to me looks fairly kind of randomly distributed. And so I'm kind of happy with that. But then we've still got this sort of weird set of data points here, which is clearly not randomly distributed. And so I suspect that there is still some kind of like systematic bias in our estimation, because you shouldn't be seeing this type of thing happening. So when we go in and kind of investigate a little bit more closely, you could actually identify these specific points. And the way that I would do that is I would look at, I could essentially go in and isolate all of these points and see if there's anything in common about this. You can filter for these points by, making an arbitrary line and saying, okay, what are all the points below that line? And it turns out that all of these guys are having to do with really, really sort of low income. And so these earnings are like less than like $2,000, $1,500 a year. And oftentimes you can actually understand the context of this if you look into the data. This could be like, people who are maybe like babysitting or held a job for a really short period of time, or doing like a sort of side hobby occupation type of thing, where the income is sort of really sort of structurally different from a lot of these other incomes that are coming from sort of regular jobs in some sense. And so if I were to kind of say, okay, let's run a regression on quote unquote ordinary jobs as opposed to people with side jobs, and let's get rid of these points, will that then improve our regression? And again, I am eliminating points here, but we're recontextualizing what it is that we're kind of fitting. Okay, and so this is gonna be, I'm just gonna do the same thing. Education, age, gender. And now the data that I'm putting in, I'm going to create a filter where I'm going to say I'm only going to include data where people are earning more than $1,500 a year. And summary of wage model log. All right. Some of these values actually look a little different. So this actually went down from like 0.99 down to 0.44. The other ones look relatively similar, right? 0.12, 0.009. Okay, so it's actually down 25%, 0.009. This one's actually almost identical. And the R squared doesn't change much, but if we plot the residuals, we can see we've gotten rid of that kind of weird line thing. And this I would say is a fairly decent set of residuals. It might be a little bottom heavy, but for the most part, I'm much happier with this plot than the previous one. Okay, so there is a little bit more that we're going to talk about with the wages and getting back to the interpretation of the categorical variables and and actually the next thing we'll do is talk about the interaction variables. But I did want to give some time, since I promised to talk about homeworks. We can spend some time to do that. Let's see. Yeah. So on Wednesday, we're going to pick up where we left off here and finish up talking about this sort of practical example and application of this. Before I answer questions about the homework, there's one thing that I actually did want to clarify, because I don't think it was entirely clear. So on homework 1, problem 4, the Claire data. So this is the raw data. The fuel amounts that you see here in this sort of quote unquote column is the fuel required per trip. And then the mileages here is different from what was being reported in the Doris data set. This mileage is the odometer reading, so it's the cumulative miles. And then the other thing that I think was confusing for some people is that when we're referring to the MPG and fuel efficiency, it's a little tricky in this context because it's like it drives both electric and gasoline, but I just want to make it sort of simplified as possible. So we're just gonna think about it as just gasoline for now, which is the way that the car actually reports the fuel efficiency anyways. So we're just kind of comparing our measurement with the car's measurement. So you're going to create another column of average MPG, and you're going to compare it to this fuel efficiency, to all of these, and see how close it is. And so the way that you want to do that is your cumulative miles divided by the total amount of gasoline. So the first one should be the same. So it'd be 770 divided by 6.22, but the second one is going to be 1276 divided by 6.22 plus 6.252. And the third one is going to be 1647 divided by 6.22, 6.252 plus 6.566. Okay, so the easiest way to do that is you can create a new column that is the cumulative amount of fuel that is being used. And there's a really simple function for that. It's called the cumulative sum. So the cum sum like this. And the way this function works is if I put in as an input 1, 2, 3, 4, 5, the output will be 1, 3, 6, 10, 15. It will create a vector that adds everything entry by entry cumulatively for you. So that's a really easy way of making that column. So, okay, so hopefully that clarifies any confusion about this. So the way that we're asking to measure and that the car measures it is basically miles divided by total fuel, gasoline used, even if you drive on electricity. Okay, yeah, so for anyone who wants to stick around to talk about homework, I can spend a couple minutes to do that. Otherwise, I will see you guys on Wednesday. And remember that the first homeworks are going to be due this Wednesday at midnight. Okay.